Hi everyone, this lecture is going to be about frequency distributions, graphs, and descriptive statistics. So the sort of general order that we'll talk about things are just that, frequency distributions and graphs. And then when we get into descriptive statistics, this is really about measures of central tendency. So that'll come at the end of our talk today. So a frequency is really nothing more than the number of times a value of a given variable appears in the data. Let me illustrate this for you real quick. So imagine you've got a class of 30 students, and I'm just sort of picking 30 out of thin air for an example. We could ask all kinds of questions about those 30 people. How many are men? How many are women? How many are maybe graduate students? How many are undergraduate students? How many live in Erie County, which is where Buffalo is? How many live in live in some other county of New York State? How many lived outside of New York State? Right, and so the number of different questions we could ask is pretty limitless. And that would simply be a way to get to know our data, which is really simply a way to get to know the people in class. We could ask all kinds of questions like, what is a person's favorite pizza topping, right? And we can answer that for all 30 people in the class, and we could count the number of people who like pepperoni or the number of people who like mushrooms, or the number of people who don't like any topping on their pizza, right? And we could just sort of go on and on. When we put that information into a table, we call that a frequency distribution, and that's just I've got an example here on the bottom of the screen. So in this example, we've got, say, 82 people. Maybe this is a class, maybe this is a community, right? Maybe this is just a group of people or people who work for an organization. And in this hypothetical example, the male value occurs 23 times and the female value occurs 59 times. And you add those two numbers up, that gets us to 82. So, excuse me. The way we do this, typically for nominal level data, we just calculate it directly from the data. You count up all the different variables. I usually make a table. You can do it by hand. You can do it in Excel. Make a table just like the one you see on the screen here, and just sort of fill it in. When you get into ordinal data or higher, it's easiest usually to sort the data. I will show you how to do that in another lecture, and then just simply count it up, right? So here we have an example of an ordinal set of data. And the ordinal, that variable in this case is education, and so we've got 5 different categories: 9 to 11th grade, high school diploma or GED, some college, a 2-year degree, or a 4-year degree or higher. We can assume that the question that went with this data probably was something like, what's the highest, or what category best describes the highest level of education that you've completed? 9th to 11th grade, high school diploma, that kind of thing. And this is a good example of an ordinal variable, although it's an imperfect example. But as we can see here, 2 people endorsed 9th to 11th grade as sort of their highest level of education. Completed 19 people endorsed high school diploma or GED, 22 endorsed some college, 10 people endorsed a 2-year degree, and 27 people endorsed a 4-year degree or higher. So there's these other 2 words called absolute frequency and cumulative frequency. The absolute frequency is simply the number of times each value occurs, and so the absolute frequency is what we saw on the first 2 examples on these previous slides here. The frequency for males and females on that first slide, and then that education level on that second slide. And so the absolute frequency is just the number of times that they occur, and then the cumulative frequency is the number of times or excuse me, the number of cases underneath a certain value. And so really mathematically, the cumulative frequency is just the sum of the frequencies below it. And so the total and the absolute frequency will add up to the last category in the cumulative frequency. You can sort of see that here. So this uses the same data as on that previous slide with education level. 2 people had 9th to 11th grade, 19 people had high school diploma or GED. So the cumulative frequency, from 9th to 11th grade is 2 people still. It's the same as the absolute frequency because there's no one sort of underneath them. But then the cumulative frequency when we incorporate high school diploma in GED is 21. And that's simply the sum of the number of people who have a high school diploma or a GED and the number of people who endorsed 9th grade to 11th grade. So the math is 19 plus 2, which gets us to 21, right? And that's sort of the same for all the remaining categories as well. The nice thing about doing tables like this is that you can sort of check the math, and because things should all add up. This is essentially just a different way of slicing and dicing data. So let me move myself real quick so we can see this. We can also express frequency as a percentage. This is you get the same idea here. There's an absolute percentage, which is the percentage of the total sample that has a certain value. And then a cumulative percentage, which is the percentage of cases that simply fall underneath a certain value. And I've done that math for you here on this slide. You can see the cumulative and the absolute percentages. Now note, if we were to, I'll put my cursor on it here, if we were to add up all of the numbers in the absolute frequency, we would get to 80, which is the same as this number here, right? If we were to add up all of the percents and the absolute percents, right, we get 3 plus 24 plus 28 plus 13 plus 34, we would get to 100% because that describes all of the cases, just as cumulative percent here adds up to 100. So how do we calculate cumulative frequency? In this case, 3% would be 2 divided by 80, right? We would get absolute frequency, same thing, 2 divided by 80. We would get 3%. If we were going to calculate the 24% for absolute frequency, we would divide 19 by 80. That would get us 24. And if we were to calculate, if we wanted to calculate this cumulative percentage here, we would simply add, or we would simply take the cumulative frequency and divide it by the total number of people. So we could do that with this number, right, 21 divided by 80, or we could add these two, 19 plus 2, which gets us to 21, and divide that by 80, which would get us, again, to that 26%. So again, this is all the same information. It's just sort of slicing and dicing it in different ways. It's just sort of thinking about it in different ways. Why would we want to ask questions like this? Well, we might want to know which segment of our 80 people have the highest education, right? We might want to know who's, how many people have the highest level of education. And expressed as a percentage, expressed as an absolute percentage, right? This tells us that about 1/3 of people in whatever this data set would be have a 4-year degree or higher. That might be useful for us, to us for some reason. On the other hand, maybe we were looking at something to do with reading level or some technical skill, and we were concerned that people who had a high school diploma or less, might need some extra assistance or some extra attention from some instructor or something like that. And so maybe we were planning, we were trying to plan a class or an intervention or a training or something like that. And so we're thinking, okay, we have 80 people coming, 21 of them are people that we think need this, whatever this extra attention is. So that's about a quarter of them. That's 26% of them. So we're going to pay special attention to them for some, for whatever it is we're doing. Okay, moving on. Let me move my picture back down here so we can keep going. So the absolute frequency, number of times each value occurs, typically we sort the data from highest to lowest. We count the number of cases in each value. You can do this by hand. You can also ask Excel to do it or SPSS to do it for you. And then note the way to check yourself here is that the total of the absolute frequency column should equal the total number of cases. And that's assuming there's no missing data. If there's missing data, you have to factor that in as well. So the cumulative frequency is the number of cases that occur under a certain value. So to calculate that, again, we're adding the absolute frequency of each value that comes above that one or before it. And then the cumulative frequency for the last value should equal the total number of cases. Again, that's sort of how we check ourselves here. For the absolute percentage, we divide the absolute frequency by the total sample size and then multiply by 100. If you don't multiply by 100, you have a decimal. In fractions, I'm sorry, percentages are just decimals. The sum of the absolute should equal to 100. There might be some rounding error, so it should be pretty darn close. But within some reasonable rounding error. And then, for the cumulative percentage, we add up the number of absolute percentage before that value, and then again that should equal 100 as well. It should be pretty darn close. Again, allowing for a little bit of rounding error. So this is, let me put myself over here. So this is a grouped frequency distribution. It's often a little bit easier to understand if we sort of condense scale variables or linear variables or ratio variables into different categories. So, for example, we might take age and divide it into the categories I've listed here. These are pretty arbitrary, but 18 to 29, right? 30 to 54, 55 to 64, 65 to 74, 75 to 94. And as you can see, this data set is quite a bit larger than the one we were using before. The hypothetical one before had 80 people in it, but this one has over 6,000 people in it. And so all of a sudden thinking about it in terms of percentages or cumulative percentages is a little bit easier to sort of digest and get your mind around it. Okay, so let's talk about graphs. Graphs. Excuse me. Graphs make a point quickly and dramatically. They can also be a little confusing and misleading. So we're going to spend a few minutes talking about the different kinds of graphs here. The type of graph that you choose really has to be based on the level of measurement of the variable. So for bar graphs, let me just move myself over there. Okay, so for bar graphs, you're typically you have data that's at the nominal level, right? Nominal or categorical level of data. And here's a good example, and I'll move myself over again, right? So this is again just there's two categories. You've got males, you've got females. Obviously, the female value occurred 8 times in this particular data set, and the male value occurred 17 times. If we wanted to know how many people were in this data set, we would simply add 17 to 8, and that would give us the total. Why would we use something like this? If we were presenting to a group of stakeholders or a group of people, and we just were wanting to sort of illustrate a point real quick, this shows us that there are sort of dramatically more males in this particular data set than there are females. Another type of graph is a pie chart. You've probably seen pie charts before. You've got an example here for you in a second. Pie charts are useful when you've got data at the nominal level as well. If you get too many categories, it gets pretty complicated. I find that pie charts are best when the proportions are fairly distinct and fairly large, and there's a fairly small number of groups. So, for example, it's pretty hard to distinguish like 34% from 37%. But on the other hand, it would be pretty easy to distinguish, say, 10% from 50%. So, graphs, there's a little bit of a judgment call with these, as always. The other thing that pie charts don't do, I'll talk about this one that's on the screen here in a second. The other thing they don't do is they don't tell us about the total, right? Bar graphs tell us something about the total number of people in the data, but pie charts do not. So this is actually that same data just represented in a pie chart, and obviously the point is made that there are sort of dramatically more males in this data set than there are females, but we don't know how many are in the data set altogether. There could be 10 people, there could be 10,000 people. And so again, this is sort of where you have to use your judgment when you're making graphs. Histograms. Histograms are useful for ordinal or interval or ratio level data. The sequence of values displayed in the graph is typically a function of the order of values or categories. You sort of typically order them from highest to lowest or most to least, or strongly disagree to strongly agree. Some way that sort of makes sense for the data. So here's let me put myself up here so we can see this. So here's an example that uses age. This is actually that same data from before, where there were sort of 6,000 people. It's just represented a different way, right? So you can sort of see this is a good way to represent a large volume of data when you've also got a large range of data, or a large range of potential values. So we use frequency polygons again with interval ratio data. We typically would use a histogram, and that makes a frequency polygon fairly similar to a histogram. It sort of reflects the shape of the distribution. It connects the bars to the tops of the line that you'll see on the next slide here in a second. But that also gets us into sort of a related concept, which is to start preparing data for analysis as well. So this would be an example of a frequency polygon. It's very similar to a line graph. Line graphs typically would represent some kind of linear variable, as opposed to a variable like this, which is much more ordinal. But again, this sort of connects to the concept that we're going to talk about next, which is the shape of distributions. Let me just put myself down at the bottom here. So the distribution refers to sort of the shape of the data. We've seen a couple of distributions already. We saw that age one a couple of slides ago. But it really refers to a set of values on a variable that have been arranged from highest to lowest, or most to least, or something like that. Graphs and descriptive statistics help us determine sort of the shape of that distribution. So the normal distribution is one of the most frequently used, I guess. It's also the one on which most statistics are based. Most statistics assume sort of this normal distribution. So in a normal distribution, it's basically a name for a set of distributions that have the same general shape. The normal distribution is symmetrical, with scores concentrated in the middle, or sort of concentrated around the mean. And there are very few scores at the tails or at the extremes. You sometimes hear normal distributions called the student distribution, or the bell-shaped distribution, the bell curve, that kind of thing. Student was actually, when you see a student's distribution, student was actually a pseudonym of the person who was sort of writing about this in the 19th century. And normal distributions really only apply to interval and ratio level data only. So here's a couple of examples of some normal distributions, and let me put myself up here so you can see all of these. So these are just examples of different normal distributions. This one is probably the most typical here. There's very few scores at the tail. Most scores would be concentrated sort of around the mean. If we contrast this one with, say, this one, this one would have a much larger range of scores, but it's still normally distributed, with most scores falling around the mean, and very few scores sort of occurring at the extremes. This one, same kind of thing. This one probably has a smaller range, and it has a lower mean, but again, it follows the normal distribution. Most scores are concentrated at the mean. There's very few scores at either of the tails, either the extreme high or the extreme low. And then this one simply means that there's a very high mean and a very limited, a very small range of scores, high to low scores. But again, this is also a normal distribution. Most scores concentrated at the mean, and very few scores at either tail or either extreme. Skewed distributions occur when you frankly have a distribution that isn't normal, right? So it sort of inverts the mean and places most scores at one of the tails, at either of the tails. So a positive skew occurs when the most values occur at the low end of things, and a negative skew occurs when most of the values, or the mean, would be towards the high end of things. Why is the direction reversed, right? Why is a positive skew sort of denote a shape where most of the values are low? Well, that's because the tail, the positive skew actually refers to the tail, and in this case, the tail is very high. And again, same thing with the negative skew. In this case, the tails are simply very low. Okay, so that's a skewed distribution. So let's talk about measures of central tendency, which is otherwise known as descriptive statistics. So a measure of central tendency is simply a value or a series of values that describe a typical score in a sample. It's sort of those numbers that are most representative of the distribution of values over a given variable. Measures of variability, which are also sort of included in descriptive statistics, simply tell us how much a variable is spread out from that typical score. So things like a standard deviation would be a measure of variability, and a standard deviation simply tells us how far apart scores are from a mean. So a couple of other examples here for you in a second. Let me put myself down here. So first measure of central tendency here, the mode. That's the value that occurs most frequently. Excuse me. The value of a variable that occurs most frequently. Occasionally you hear the term bimodal, and that simply means that there are more than one value that occurs more frequently than all the other values. You could have, like, give you an example here real quick. Let's say we had in a class of 30 people, the two most common ages of a class of ages in a class of 30 people were 27 and 30. I'm just sort of picking these out of thin air here. If those numbers occurred sort of with the same frequency and more than all the other agencies or all the other ages, we would say that there's a bimodal distribution. Mode can be used with other measures of central tendency, or it can be used with all levels of measurement. It's probably used less often than other measures of central tendency. So identifying the mode on a histogram is actually very easy. It's simply the highest bar. One of the advantages of using the mode as a measure of central tendency is that it's really not impacted by outliers, but it's also not widely used and it's not necessarily unique. If we were going to calculate the mode from the data on the screen here, which is 3, 4, 5, 5, 5, 7, and 9, 5 occurs more frequently than any of the others on there. So 5 is the mode of those 7 values there. Median is sort of the midpoint. So that's the value at which half the values fall below and half the values fall above. Best way to calculate the median: sort the values and then sort of identify the one that comes in the middle. If it's an odd number of cases, it'll be sort of exactly in the middle. If it's an even number, it's the average of the two most central values. If you want to use the median, you have to have ordinal data. And one of the nice things about the median is that this is it's also not affected generally by outliers. So median, it's the middle. It's again not as popular as others. And if we were to take that same sort of cluster of 7 numbers, 3, 4, 5, 5, 5, 7, and 9, because this is an odd number of values, it's simply the number that's in the middle, and in this case, the number that's in the middle is 5. So these set of values have the same mode as they do the median. So the mean is third. Let me just move myself down there. Third measure of central tendency. That's adding up all of the numbers and dividing by the total number of values. It's simply the average, something that most of us are probably familiar with. Mean can only be used when we have interval or ratio level data, and one of its disadvantages is it can be distorted by outliers. The mean is pretty widely used, but again, it's really sensitive to those outliers. So if you have a really small data set, and particularly an outlier that's really extreme, it sort of would distort the mean. And in that case, one of the other measures of central tendency would be a good thing to use. So let's talk about the relationship here between the mean, median, and mode. When we have a normal distribution, which is what this top graph represents right here, when we have a normal distribution, the mean, the median, and the mode are all the same number. So it actually doesn't matter which of those you used to represent the data. They're all the same. And that's sort of what makes the normal distribution so desirable or sort of useful for statistical analyses. What we see in research often is that, particularly in social work research, where we're dealing with vulnerabilities or sort of the effects of injustice and oppression and things like that, is that we often see data that are skewed. So if we were to look at a positive skew, and remember a positive skew is data where most of them are clustered on with low scores, right? The positive skew refers to where the tail is. What we see is that the mean, median, and mode all of a sudden are very different. The mode occurs most frequently, but it's actually much lower than the mean. Same thing with the median. That's the one that's in the middle, but it's higher than the mode, and it's lower than the mean. So which one do you use here? Typically, you would use the median. Same thing with with a negative skew, the mode is typically is going to be the number that occurs most frequently. So that's at the high point of the curve, but it's much higher than the median and the mean. So typically when you have skewed data like this, what people report is the median. You hear this sometimes on the news when some commentator or news person is talking about income or something like that. Typically they would report the median as opposed to one of the other numbers. So measures of variability. I'll put myself down here. So the range is simply the distance from the lowest value to the highest value. The range can only be used with interval or ratio values, and to calculate it, it's simply the maximum value minus the minimum value, and then you add 1 to that. So it's often reported as, the range of data, went from, whatever the lowest value was to the highest value. But that is a measure of variability. Another measure of variability that we hear about quite frequently is the standard deviation, and that tells us to what degree values cluster around the mean. You can only use standard deviation for interval and ratio level data. And here we go. Whoops, I guess I'll put myself here. Here, let's talk about standard deviation in relationship to the normal distribution. So if we have a normal distribution here, and then we have one standard deviation. Okay, well, let me back up. So we have a normal distribution. The mean, median, and mode would all be at the highest point of the curve. And what I've represented here with a dotted line are a standard deviation above the mean and a standard deviation below the mean. What is so useful about a normal distribution is that 68% of all scores would occur between a standard deviation below the mean and a standard deviation above the mean. And so that actually captures, just about 2/3, a little more than 2/3 of the scores in a given data set. This again is why the normal distribution is so useful and so it was actually very important to sort of the development of statistics. If we extend it out to 2 standard deviations, we're actually encompassing 95% of scores, so nearly everyone. So if we had some normally distributed variable, let's say something like height. If we had a huge sample of people, say 10,000 people or something like that, we'd probably get we were able to get all of their heights. We would probably get a normal distribution. And then if we were to pick another person at random, there's a 95% chance they're going to occur in, their height is going to be within 2 standard deviations of the mean. So it's very unlikely that we're going to get, a basketball player or something like that who's going to be really, really, really tall. Or on the other hand, we're going to get someone who's very, 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 very short. Very unlikely, right? Because this is sort of the normal distribution. So this is where most of the scores fall. If we extend it out to 3 standard deviations, you actually get 99.7% of scores occurring within 3 standard deviations. Let me put myself down here. So there's some precise rules for a standard deviation. 95% of values are 1.96 standard deviations above or below the mean, and then 99% of values are 2.58 standard deviations above or below the mean. And these values will become meaningful here when we start to look at p-values and when we start to do some significance testing over the course of the next couple of weeks here. So this is what we talked about. The things to sort of focus on are measures of central tendency. You should know what the mean, median, and mode are and how you calculate them. And then we've talked about two measures of variability, and that's the range and the standard deviation. At this point, we haven't talked about how you calculate these, or we haven't talked about how you calculate the standard deviation. We have talked about how you calculate the mean, the median, the mode, and the range. We will get to talking about the standard deviation here more in future weeks. So, all right, if you have any questions, feel free to let me know. Thanks for watching.